Hello friends, in this video we are going to discuss about the Fermi-Dirac statistics that is applied in the semiconductor. So the Fermi-Dirac statistics in the semiconductor is used to find the distribution of electrons inside the semiconductor in different energy levels. So let us see what is Fermi-Dirac statistics. So this Fermi-Dirac statistics is also called as Fermi-Dirac probability distribution function. In short, we can call it as FD statistics. Now, this FD statistics is given by the scientist named Fermi and Dirac. So, this statistics gives a equation like this: F of E and T is equals to 1 by 1 plus exponential to the power E minus EF by KT, where E is the energy possessed by the electrons at some given temperature T. Now, if I look at this equation, then what is the physical significance of this equation? So, the physical significance of this equation looks like this. For that, let us consider the band diagram of the semiconductor. So, in the band diagram, we know that there will be some conduction band and there will be a valence band. So, this is our conduction band and this is our valence band, where this EC is the minimum energy level inside the conduction band and EV is the maximum energy level inside the valence band, and this gap is the energy band gap of the semiconductors, and there are so many energy levels inside the conduction band as well as the valence band. So, these dotted lines are the energy levels inside the valence band and conduction band. Now, this equation gives that what will be the probability of finding an electron at any energy state at any temperature T. That is, let us consider a energy level, this one, as E1. Now, suppose we want to find the probability of finding an electron at this energy level E at this energy level E1 at some temperature T. So, this value of the probability will be given by the function f of E1 comma T. So, this f of E1 comma T can be written as using this equation like this: f of E1 comma T is equals to 1 by 1 plus exponential E1 minus EF divided by KT. So, we can see that from this equation we can find the probability of getting an electron at any energy state E in the conduction band at some temperature capital T. So, from this equation we can conclude some several statements. So, let us look at the several statements. So, the first statement that we can conclude that this function for FET, that is the Fermi-Dirac function, is a strong function of temperature. So, the second statement is that the Fermi-Dirac function FET will increase with the increase of temperature. So, the third one statement that can be concluded is that Fe T, that is the Fermi-Dirac distribution function, specifies the fraction of all state at energy capital E occupied under the thermal equilibrium. And the fourth statement that we can conclude here, F E T gives the probability of finding an electron at any energy level capital E at some given temperature capital T. The fifth statement that we can conclude that FET does not indicate how many electrons are residing at the energy level E at some temperature capital T. That is, FET will not give the number of electrons that are residing at the energy level E at some given temperature T, but it will only provide the probability value of getting the electron at that energy level E at some temperature T. And the sixth conclusion that can be drawn, that FET will not provide how many energy states are occupied by the electrons. So, these are the conclusion that can be drawn from this Fermi-Dirac statistics. Now, let us look at the Fermi-Dirac statistics at different value of temperature. So, FET can be found at different value at different temperature. So, let us take the first case, that the temperature is at T equals to 0 Kelvin. So, at T equals to 0 Kelvin, if I find the value of FET, the equation will look like this. Fe of T can be written as 1 by 1 plus exponential E minus EF by K into T. Now, if we look at this equation, we can see that there can be two conditions from this equation at temperature T equals to 0 K. The first condition is that if the energy level is less than the EF, which is the Fermi energy level, and if the energy level capital E is greater than the Fermi energy level EF. So, let us take the first condition, that the energy level capital E is less than EF. So, if the energy level is less than the Fermi level, then the Fe equation at T equals to 0 K can be written as 1 by 1 plus exponential, and this E minus EF will be a negative value because E is less than EF. So, there will be a negative value, and here T value is 0. So, it will be 0. Ultimately, we will get 1 plus e to the power minus infinite, and we know that e to the power minus infinite is nothing but 1 by 1 plus, it will be 0. So, I am getting a value of 1 here. That means we can write in statement that at T equals to 0 Kelvin, the probability of finding an electron at any energy state capital E, which is less than the Fermi level, that is EF, is always 1. That means we will get a electron surely at that energy level which is less than the Fermi level at temperature equals to 0 K. Now let us look at the condition if the energy level is greater than the EF, then what will happen. So let us take the condition B, that energy level is greater than EF. So the value of the function f e of t, and t is at 0 K. So I can write the equation like this: 1 plus exponential e minus ef part in the numerator will be positive because this capital E is greater than EF. So it will have a positive value, and in the denominator we will have a 0 because temperature is equals to 0. So we can write this equation as 1 by 1 plus e to the power plus infinite, and e to the power plus infinite is equals to infinite. So finally we will get 1 by infinite, that is equals to 0. That means the probability of finding an electron at any energy state E which is greater than the Fermi level that is capital EF is always 0 at temperature equals to 0 K. So if we depict this conclusion inside the energy band diagram, so it will look like this. So in the energy band diagram, this is the conduction band and this is the valence band, and this is the value of EC, and this is the energy level EV. And let us consider that we have taken an intrinsic Fermi level. So we can say that the Fermi level of the intrinsic material will be near at the middle of the band gap. So this is the Fermi level for intrinsic material, and the band gap is this value. So we can say that in the conduction band there are so many energy levels. So the energy levels are these one, the dotted lines in the black color, and all these energy level are above the Fermi level. So we can say the energy level in the conduction band is greater than the Fermi level EFI. Similarly, there will be some energy level inside the valence band also. So, let us draw that energy level inside the valence band. So, these are the energy levels inside the valence band. The red dotted lines, and all these red dotted lines are less than the Fermi level inside the intrinsic semiconductor. Now, we know that the electrons are always reside on the conduction band. So, now if we want to find the probability of the energy levels of finding the electrons in the conduction band at temperature T equals to 0, then it will be exactly 0. That means Fe T for all the energy levels in the conduction band will be 0 at temperature equals to 0 K. But the FET value for the energy levels in the valence band for all energy levels in the valence band will be 1 at temperature equals to 0 K. So, this is all about the introduction of Fermi level of the intrinsic semiconductor. Thank you.